Welcome to GLOBHE's GIS Day 2021. GLOBHE is a startup that operates with the ethos of drones for good. During this hour, we will learn how to use mapping with drone data and AI for sustainable operations in health and environment. There's also a raffle. So we will randomly select the names of 2 participants after the event, and we will provide them with 2 new ArcGIS licenses for personal use only. At the end of the presentation, there will be a Q&A section, so please ask your questions in the chat as they pop up, and we will answer them at the end of the call. Keep yourselves on mute and your video off. This will also be recorded for the presentation so that we can share it on social media after. I welcome Michael, our drone expert, and our CTO, Remy, to the stage.
Thank you very much, Emilia, and welcome everyone. So in case you don't know what GLOBHE is, we at GLOBHE have found a way to provide high quality image data to organizations and companies around the world who are looking to use drone data for a good cause. So yeah, we provide data, but we are focusing solely on drones. So the way to do it is for a company and organization to go into our website, select an exact area around the world where they want to collect data, provide us with as much detail as possible. For example, are they looking for a 3D model or a 2D map? And what is the end goal of this data? And then we set this up by connecting this request to a local drone pilot. And this is what we call crowd droning. So right now we have over 5,000 drone pilots in 90 plus countries around the world. So this is a very quick and easy way to scale up your image data. And what we've been working on lately is trying out new ways to analyze the data we actually collect. So the images themselves don't always tell the full story. You actually need to do a little bit of analysis to them, and that's what this GIS Day is all about. So what we have started with here, and I want to show you, is that we are fighting malaria through maps in Malawi. So we have done this all through the summer. So malaria, as you probably know, is a huge global problem with 200 million people affected each year, and we have over 400,000 deaths per year. And Malawi is very much affected with 4 million people diagnosed each year. And the region we have worked with is called Kazungu. And our solution is actually called vector control. So instead of waiting for the mosquitoes to become fully grown and then exterminate them, we are working on finding the spots where they breed and where they lay their eggs to actually exterminate them in an earlier stage before they become full-grown mosquitoes. So together with the Liverpool School of Tropical Medicine, we came up with this plan to map the same area of Kazungu during the summer. So we have been mapping there for 4 months, doing it once per month. And we have done it through a team of local drone pilots who are then connected to us through this crowd droning network. So the first step for our pilots is to choose the exact site where they're going. And they can draw this in a drone mapping flight planning software. And once you have that plan, you can reuse it to go to the same area time and time again. So you can see a change over time. So step 1 is planning the mission. Step 2 is going out there, capturing the data with a drone, which is super easy with most softwares. And the third step is then once you have collected all these individual images, you stitch them together into this orthomosaic map. And an orthomosaic map is a single picture, which is a high resolution image, which is the map of all of the individual drone images together. So once we have this map, we can actually start looking for certain types of areas that are ideal for mosquito breedings. So for example, it's swamps, it's shallow water, still water. areas with a lot of vegetation. So these types of areas we know before through research which areas are ideal for mosquito breeding. So what we can do, we take the same previous map that I showed before, but then we start identifying different visual elements. So this includes classifying the different types of vegetation, water types, soil, to identify the likely mosquito breeding sites. So one way to do it is manually. So what we have here is we have a person that has sat down and looked at the previous drone map that I showed and identified all the types of vegetation, and he's drawn a GIS map like this one. And this takes a lot of time, but it works for an area like this, which isn't too big. But then if you want to scale it up to a much larger area, like we did in the Kazungo area in Malawi this summer, then we need a quicker solution. And one thing you can use is AI. So we use something called a classifier algorithm that identifies the vegetation type automatically and classifies them into various groups. So then we have a really quick way to map out exactly what the environment looks like in our chosen area. So now we know exactly what the environment looks like in this area. So then we know where we can pinpoint where the perfect, the ideal mosquito breeding sites would be. So we know it's for example, the shallow water. So we draw this final map on top of the old map. So here you see the 6 different ideal mosquito breeding sites. So now we have pinpointed the exact locations. We know the exact size of these sites. And so these maps can then be sent to the local authorities or whoever is responsible for then going there and exterminating the mosquito larvae. So this has huge potential, as a lot of countries like Malawi are facing this problem, and it's not something that's going away. These ideal spots that we're looking for, they change from month to month. So for example, the project we did, we had to map it every month because as the season was getting drier, the water spots were changing. And so the breeding sites were kind of moving around between months. So if you do this continuously each month, then you can always know where are these ideal breeding sites. And that's what's called vector control. Thank you.
Thank you, Mikael, for presenting solutions in drones in the health industry. Of course, I mean, at GLOBHE, we have worked on many case studies. We have worked on many sort of verticals, such as infrastructure, health, environment, water, forestry. So we do have a lot of case studies. And what we're going to present now is basically a case study on the environment and how can we use drone maps and how can we use mapping to map flood risks and locate the areas that actually are affected or might be affected by flooding. And we're going to take also a case study from Malawi. It's simply because we have a lot of data from Malawi, and we have worked a lot in this area, and there's a lot of things to be done really to help the local communities. So a quick snapshot about Malawi is that about 85% of the population is living in rural areas. So they depend a lot on farming and a lot on agriculture. So the effect of climate change in Malawi might be really catastrophic for the local community, who is depending a lot on farming to survive, simply. Now, we did this project back in 2020, where we took some data of, again, also in the Kasungu area, and then we noticed when we took this drone image that you can see on the right, is that the river is more than 10 times wider in the rainy season than it is in the dry season. So there is significant flooding that is happening in that area. And we thought that, okay, is that something normal, or is that something that is abnormal that is happening only this year? So we had this hypothesis, and we thought, okay, if this is something abnormal, then this really might affect the local community very severely. So how can we test this hypothesis, and what can we do to help these people? So we thought that we need to measure this impact. And the way to do that, we started with a very large area by using satellite images. So there is a new tool from Google that is called Earth Engine. And for those of you who are not very familiar with Earth Engine is simply assembling all the satellite imagery that we had globally since the 1980s. From many satellites, and it's assembling them in one platform, and at the same time we have access to the Google Cloud services, so we can both access the data and also analyze the data by using the high-level computing at Google, using the Google server. Because before, people used to download all data. It used to take days to download data. It used to take days to sort out and clean the data, and so at the end, we wait a few weeks before just starting to analyze data. So that's why now we can do everything in the clouds. And this is really a game changer in the geospatial industry. So what we've done here is we looked at the satellite imagery, historic satellite imagery. We applied some algorithms to be able to clean the data and then visualize how the river is behaving through the years. And then we actually start to visualize this. So this is the result of what we did to test our hypothesis of why the river is actually changing, or is it truly changing seasonally? So we've looked at about all of these years from the 1990 till 2020, and then we applied this algorithm for the same period each year. And then what we can notice is that when we go closer to 2020, especially after 2017, the river is indeed starting to be wider. So the flooding rate is starting to be much more than the previous year. So this might be related to climate change. We have no idea. We cannot really test this. But what we know is that the river is getting wider. So this said, if we are going to have even more flooding, how is this going to impact our local communities? And to do this, we can use drone data. It's very difficult to use satellite data to do flood risk modeling, because satellite data usually has a very low resolution. So we're talking about 10, 20, 30 meters. In our case, the resolution is much lower, and we're going to see that later. So how can we measure or gather elevation data through drones? Well, the first thing is, again, we have to go and capture the data. And this map shows you all the different single images that were taken in that area by a drone. And then after that, we create this orthomosaic, pretty much like Mikael has said before on creating this orthomosaic for the malaria case. And then the drone software is going to assemble and stitch all of these images into one single image that we call an orthomosaic map. And from that map, we can create what we call a digital terrain model, which means we will have the terrain. It's like a digital elevation model, simply, that we can create from drone data. And from that model, we extract contours. This is what we call a topographic map. And for those of you who are really, who work a lot in the geospatial industry, you would recognize that immediately. But for those people who don't really have a lot of experience in geospatial data, a topographic map or contour lines, let's go into contour lines. Contour lines are usually points of equal elevation, which means that here you have the river. So this is a flat area. So we have pretty much no elevation. And then each contour is one sort of altitude. So I think, if I'm not mistaken, that should be 1,450. So the contour interval is 1 meter. So the next contour is 1,451, 1,453, and so on. So if we are in that area and we have about 20 contours, so that means we are 20 meters higher in this area than when we are in that area. So this is what a contour map is. And this is the basics, or the basis of topographic maps. Now, from that map, what we do is we try to flood it. And so what's happening here, after we generate this map, we export it to a GIS software or any other types of software as well, and we try to flood this map. So here, for example, in the blue one, this is the current sort of river. This one is in the dry season, and this one, the blue that is a little bit lighter, is the maximum flooding that we have observed in drone data. And then each shade of blue is basically the river that is sort of raising its level 1 meter after 1 meter. So you can see how it's basically filling all the other contours. And then we can keep doing that to model what is the effect of flooding is going to be and to which area the flooding is going to reach after a certain amount of time. Now, the end map, the last map that we can get from this, or the end result, is going to be when we superpose this flood modeling with, let's say, an image or a satellite or even the drone image, and also the urban plan or the map of the area or the village that is present there, which is actually in yellow. And you can see here that if we have, let's say, a flooding of the river or a river level rise of about 5 meters, the first houses that are going to be affected are right here. And these houses here will not be affected. But what we can also do is we can measure how much of the area is going to be flooded. Like this area here, for example, is about 35 meters or 35 hectares that is actually being flooded by water. So imagine that this village is going to lose 35 hectares of agricultural land, which might be quite significant for them. And this is what we can accomplish really with these elevation models. So this is another image from Fiji that is showing the high resolution elevation that you can actually have. Now, this is a digital surface model, so it takes into account not the terrain, but also all the objects that are found on the terrain, like the trees and the buildings, and you really can see the high resolutions. And when we apply these flood modeling to that, we can get really enormous amount of results. And this is something we cannot really accomplish with satellite data, because if we take, for example, the world topographic map that is about 30 meters in resolution, you will never be able to get to model such areas that, you know, we only have half a meter, or 2 meters of sea level change. So this is something that we cannot really accomplish with satellites, but we can accomplish that with drones, because these maps are extremely detailed. They can go into the millimeter scale or the millimeter resolution. And the implication of that on multiple industries is enormous. For example, if we think about search and rescue, you would know which area, or when we have a flooding, for example, we know which house has been flooded first, because we've already have done our homework, we have it on a map, so we know where to go, we know where survivors might be. But it also can be in prevention. So we know which areas are going to be flooded first. So we know we can plan, we can actually protect these areas beforehand, because they are the most vulnerable. And the same thing could happen if we think about the insurance industry, because they would know which area is riskier than the other. So it becomes better for them to put their pricing plans, and it becomes better for people to pay fair prices according to where they live. The same thing happens for the construction, for example, who would know which areas need to be strengthened, or how to better design houses and construction sites. So that's why these elevation models and these maps that we can do with drones might be a game changer in multiple industries. And this is what we really are showing at GLOBHE, and this is what we want to show to a lot of companies, a lot of authorities, that using drones is actually very beneficial for both the communities and also the companies themselves. Now, we do have multiple other story maps that we have published on malaria, but also on forestry, and we are creating much more story maps to better tell the story behind what we do at GLOBHE. How are we using maps, and how are we using drones to really benefit the society and make it better for the environment? So we'll try to send you these presentation, so you can access these maps. You could have the link and you can click on that and you can access them, and you can keep everything as a record. And if you have any questions, we would really love to answer your questions. You can ask your questions here if you click on activity, Q&A, and we would love to answer your questions. And we are always here if you like. Just send us an email. We are more than happy to answer your emails or to meet you. If you have any questions about how to use drones, how to use mapping, how to use GIS to achieve better results, both at the industrial level or basically if you just want to start your portfolio doing more maps or using drones for good like we do, you are more than welcome to just contact us and we'll be happy to help you as much as we can.
Remy said, please check out the story maps that we'll send afterwards, because they're a great visual way of understanding what drones can do for the world. So please check them out.
Yes, if there are any questions, this is the last call. Otherwise, just check out our website and the story maps. And you can always contact one of us in the Team GLOBHE, either on Instagram or on LinkedIn or wherever we are. We're on all platforms, I think. And thank you for joining us today. And this will also be recorded. So if you missed a certain point or something, or if you want to rewatch an element of the presentation, it will be up on our social media shortly. I see that there was a question from Andreas. It says, what was the software used to create flood risk modeling? Remy, do you have the answer to that?
Yes, I can definitely answer that. The best software to create these things or to create flood maps and flood modeling is ArcGIS. I definitely recommend that. Unfortunately, we do not have ArcGIS at GLOBHE, or we cannot use it commercially. So we use simply Illustrator for this. It also can work, but I definitely recommend ArcGIS to do flood modeling.
Which if you win the raffle, you will have access to. So that's great. Okay, any other questions, or shall we wrap it up here? It looks like that's about it. So thank you so much, Remy and Michael, for your wonderful presentation. And we will see you on social media or in person, perhaps. Thank you, everyone, for attending, and have a good evening or day, wherever you are in the world.
Right. Thank you so much, everyone.